Okay, so we are live. I assume that means we're recording. I assume those are synonymous. So welcome to the Gaining Efficiencies with Evidence Synthesis Tools session. I believe the best way to do this would be since all the talks are about 5 to 6 minutes apiece, to save like questions till the end of each talk, since they're only about 5-6 minutes apiece. And first up is Carole, and then I might say it the wrong way. Lunny, maybe is how to say the last name?
That's right. Thanks, Chris.
Okay, thank you. And so for that we have a video, and so I'm going to make sure I can get the audio visual correct, and we'll go ahead with our first talk.
Hello, my name is Carole Lunny with St. Michael's Hospital in Toronto, and I'll be talking today about our project to develop WISEST, which is an automated decision support algorithm to choose among systematic reviews on the same topic. Please tweet me at Carole_Lunny. And we have no conflicts of interest to declare and no funding as well. However, we would like to acknowledge the traditional, ancestral, and unceded territory of the Musqueam, Squamish, and Tsleil-Waututh nations on which this research team operates, which is out of British Columbia. So there's been an exponential growth in systematic reviews, as seen in this graph, with over 80 systematic reviews now being produced per day. This obviously leads to duplication of the same systematic reviews on similar topics. So evidence-informed practice, policy, and guideline development requires quality appraisal to choose the best evidence available. So the manual process of assessing the quality of systematic reviews using tools like AmStar2 or Robust is time-consuming, requires skill and training, and is costly. And no automated tool to date that compares systematic reviews and selects the best evidence doesn't exist. So our objectives are then to develop an AI approach to model quality appraisals for systematic reviews and to compare PICO criteria and other methods, which we call features, across these reviews. Our specific objectives are to select features that will be used to compare overlapping systematic reviews, create a labeled data set of 10,000 systematic reviews that are clustered by topic, train, test, and validate machine learning models for F-score and accuracy. So we've completed 3 preliminary studies to inform our first objective to select features to include in our models. First, we found one tool called the Haddad algorithm, which is used to choose amongst competing systematic reviews. So we tried to replicate 21 Haddad assessments by other authors, but were unable to do this. So this study is in process with the journal BMC Medical Research Methodology, which is denoted by Study 1. Study 2 was a survey we did of decision makers to determine how they compare and choose between systematic reviews on the same topics. This is denoted as Study 2 and is uploaded as a preprint. Study 3 that we did and is being analyzed right now is a qualitative study of features extracted by researchers used to identify or manage discordance across systematic reviews. We will choose the features based on studies 1 and 3, and our quality indicators will be based on AmStar2 and Robust items. So our second objective is to create a labeled data set of 10,000 systematic reviews clustered by topic. And so to do this, we approach 4 organizations who will be supplying us with 8,450 AmStar assessed systematic reviews. We'll have to identify gaps in this data set and also clean it up quite a bit. So for our third objective, our data will be split into 3 parts. The first set will be used to train our model. The second set will be used to evaluate the model's performance using F-score and accuracy. And the third set will be used to validate those models using those same indicators. So we don't want to just use the same data that our model was trained on, since it could memorize those questions just as you wouldn't use the same questions from your math homework and use them on the exam. So our steering committee made a few conceptual decisions about the WISEST tool. First, we decided that systematic reviews will be included if they focus on healthcare interventions, if they were conducted with or without meta-analysis, and could include randomized and non-randomized studies. So the way it'll work is users will upload a PDF onto our website, and then WISEST will basically extract information from that and provide it in a user-friendly interface. So in conclusion, our WISEST tool will have a large impact due to time saved compared to manual approaches and a broadened audience of decision makers who wouldn't habitually use these manual tools. The WISEST tool with functionality to extract PICO methods and other features allows for a flexible approach tailored to the needs of the user. And with WISEST, decision makers will be able to evaluate the validity and applicability of systematic reviews, thus increasing the uptake of relative evidence and ultimately improving patient outcomes. So I thank you for your attention, and I welcome any questions.
Okay,
so I'm wondering, Chris, can I just take questions now since I'm going to have to leave early?
Yeah, I had planned for after each talk we could pause for questions. So yeah, were there any questions for Carole?
I guess I have a question. I don't know how to raise my hand, so can I just ask it?
Sure.
Carole, are you looking at a specific type of systematic review, like systematic reviews of effect, or are you going to look at across different types of systematic reviews?
Well, I think we're going to start off by just making it systematic reviews of interventions, but I think we would like to make it broad. So for every systematic review out there in every field, because I see that it's going to be hard to make it specific to different contexts if they have different ways of, say, for example, analyzing data. But so we'll start off like on the, we're in medicine. So I'm in medicine, so I'm going to start off with that. I think we want to move on to social and humanities as well. We have data sets from there as well. And I think somebody is the tool free, and it will be free, yes.
Thank you for that. Any more questions? I see Jan has his hand raised.
Yeah, if I may, could you just briefly explain? You said that you were training, but it wasn't entirely clear to me what sort of stuff you were training on. Are you looking into NLP methods, so natural language processing, or what sort of algorithms are you exactly looking at?
Yeah, for now we're testing two models, which will be random tree, which is a natural language processing, and then deep learning. So those two to see which model works best with our data. And I think somebody asked, is there any kind of prioritization exercise? So to identify topics or questions where there are no high quality reviews. And so I think that's a great question, because we really need good data for our models. So which means that we need systematic reviews with really correct answers because we don't want the model to think that a bad answer is the correct answer, right? So we might even have to make up dummy, systematic reviews with what we think of as perfect data. I'm not sure how that's going to work, to be honest. Or we're just going to have to keep extracting until we get, really great reviews, which I think might be hard.
Perfect. Well, thank you so much. I believe so. Our next talk I have down is coming from Jan, although I think that we're going to switch the presenters. Is that correct?
No, that was after me. It's Max Callaghan.
After, okay.
Yeah.
Okay, gotcha. Well, yeah,
so
you're up next.
I'm happy to Let me just go there. Can you see my screen?
Yes, we can.
Okay, excellent. Yeah, so I will be talking briefly about AI for automated living evidence maps on climate solutions. Let me just put on my timer. So yeah, the idea behind this was that we were trying to track publications in the field of climate and health that are really widely spread out across different communities, and it's really impossible by now to keep really an overview. So we wanted to create a systematic map, and doing this by hand, because it's a broader field, is impossible. So we wanted to develop a machine learning pipeline that can, in principle, be, if possible, fully automated. And that we would still try to be in line with existing reporting guidelines. But of course, not everything there is defined, but document everything, at least in a published protocol that would take those machine learning elements into it. And now we are currently thinking about developing a living evidence map from this. So the study that I'm referring to was led by Leah Barang-Ford from the University of Leeds, and carried out in collaboration with colleagues from the London School of Hygiene and Tropical Medicine. We at MCC were mainly in charge of the methodology, of the machine learning methodology. So on the left-hand side is the protocol, right-hand side the systematic map for anybody who is interested. This indicator that we derived is now also part of the upcoming Lancet Countdown publications. So what sort of process did we do? And so I'm just going through the chain of the process chain in systematic mapping. So we started from a question and protocol. Then we did a broad search in 3 databases, Web of Science, Scopus, and Medline. We designed a broad string around keywords from climate, weather, and health outcomes, which brought us about 290,000 papers or bibliographic entries back. We screened 3,730 of them, title, abstract, keywords level, and labeled for inclusion on the one hand, and then we classified them in 3 categories: climate impacts, mitigation, and adaptation. We then went into a stage of prediction, and we predicted inclusion with the support vector machine using a 50% threshold. So if a paper had a 50% probability of being relevant, we decided to include it in the later implementation, interactive implementation. We were using flexible thresholds for users. And those
may I just interrupt? We don't see your screen. We only see the starting page or the starting slide of your.
That is too bad. I had this problem before, and we tried it before, and it was working. Can you see it now? No?
No, we can't.
Okay, then I guess I have to unshare.
We did before. They just weren't progressing.
Okay. Can you see it? Now also advancing?
Yes, we can. Yeah, you're on slide 4 now.
Yeah, exactly. On predictions. So we did that, and then we used this inclusion to predict out of the 290,000 those that are likely to be relevant, so which came out to be about 16,000 studies. And then we used also a support vector machine to predict the label climate impacts, mitigation, and adaptation. And we ran a topic model for additional labeling, and we extracted locations, so the study areas or the areas, the geographical focus of the study for all those 16,000. Then we went into an analysis stage, clustered super topics, developed a topic map using t-SNE algorithm, and then did various things in visualization, produced an interactive website Can you still see the slide advancing? Now I'm on the next slide. Can you see that?
You're still on the process slide.
Okay. Yeah, so it's really not working.
Okay, now you're on the next slide, but
okay. So I probably I'm really sorry for this. Yeah, so just a view of the outcomes. So this is the literature, how it develops over time. So what we see is that the vast majority of the literature in climate and health is really on climate impacts. Only a smaller share is with a focus on solutions. Here, the next slide also gives you a view of the locations of studies where we see a real clustering in Europe, Asia, particularly Eastern Asia and North America, with potential knowledge gaps around South America, Africa. And then we see on the right-hand side that for all these kind of, for all the continents, for example, we can really say how the studies, for example, talk distinctively about health risks, mediating pathways or options of responses. We created an interactive website, so as a community resource. And just to finish up some closing thoughts, how we now want to move ahead towards a living map. So one is that the pipeline that we developed is almost fully automated, but still there are many important aspects to be defined in a living evidence world. So the update frequency, when to publish a new version, I think that is not necessarily straightforward. When is it worthwhile to come up with the next version of the map and publish that again? What is the authorship of this? How long can we use a topic model, for example, that is estimated before it's basically getting dated? How can we make sure that we detect new topics as we are going along with the same pipeline? And I think these are all questions that will need to be answered if we are really serious about mapping out in a more automated way broader fields. Of course, we also pay a price of automation in terms of the precision recall. There's a real trade-off that we have to do. To date, it's still unclear how gold standard reporting guideline for such a map would look like in such an automation work. And I think there's an important work to be done. Validation, I think, is a key aspect, particularly for unsupervised machine learning approaches. Other issues are around gray lit, how we can get that in non-English literature. We were really focused on English texts and full text. So I think working with title abstracts is actually not a bug but a feature in the context we did it. But if we want to do other relevant classifications, for example, around methods, we need really to go into full text, and there are a whole range of aspects that need to be considered. I leave it here for the matters of time. Thanks so much.
Great, thank you so much for a great talk. I believe we're doing actually pretty well on time. Were there any questions? And I'll make sure to look in the live Q&A too. Thank you for that.
I mean, maybe with regard, if I understand the question by Kate correctly, I mean, what we did was to combine a world of, doing some direct screening and then predicting from that using a supervised machine learning approach, and then combining it with topic modeling, right? So we would not right away go from the search query to the topic model, but rather we would make sure that we can predict relevance in the first instance based on human labels with a high accuracy, and then move on into the more automated into the unsupervised tasks. So that would be one answer.
Makes sense. Any more questions at this time? Okay, well, if there aren't any more at this time, then our next talk is going to be from Finn. The floor is yours.
Thank you very much. Can you see my slides? Yes.
Yes, we can.
Okay, so I'm actually Finn Müller-Hansen, not the one that was initially on the agenda. Max Callaghan is the first author of this paper that I'm presenting today. And we are looking at statistical stopping criteria for automated screening and systematic reviews. We are interested in machine learning assisted document screening. So at the first stage of a systematic review, how can actually machine learning help to reduce the amount of work that we need to put into screening whether documents are relevant or not. And there's actually a growing number of machine learning applications that do exactly this. They help screening documents. And by using machine learning that prioritize documents that are likely to be relevant, we can actually, in theory, achieve high levels of recall without screening all the documents in a set that could eventually be relevant. However, we usually do not know a priori the true number of relevant documents in that set. And we need some criterion when to stop the screening process. If we are stopping too early such a process, this can actually lead to huge biases in the reviews, because then only a small part of the actual relevant documents will be included in the review. So we came up with the following stopping criterion. So we started thinking about this as, in very simple terms, as an urn where we have white and red marbles corresponding to not relevant or relevant documents. And we actually draw randomly from this urn without replacement. And this is described actually by the hypergeometric distribution, which gives us the probability of observing a certain number of red marbles in a subset of our full set of potentially relevant documents. Using this hypergeometric distribution, we formulate a null hypothesis that a given recall target, for example, we want to include at least 95% of all relevant documents, that this has been missed. And then we derive with some calculus a p-score for rejecting this null hypothesis. And by this, we can actually stop screening if this p-score is actually below a certain threshold, so that we can be confident that the null hypothesis can be rejected. Maybe just as a side note, the machine learning usually prioritizes documents to be seen earlier that have a higher probability of being relevant. So this makes our test conservative, because we assume that this will be drawn at random, but in the machine learning process, actually those have higher priorities that are more relevant or more likely to be relevant. So we test this statistical stopping criterion with a sample of 20 complete systematic review data sets where we have the labels actually, and we set up a simulation that somehow replicates how such a review then would uncover these labels. First of all, as you can see here on the right, the theoretically achievable work savings in the data set varies quite strongly, because the proportion of relevant documents in the sets are very different. And now we compare this to existing stopping criteria from the literature, for which a lot of them actually yield very low recall. Here we can see the example of a heuristic using 50 consecutive irrelevant articles. And there's another example using some estimated baseline inclusion rate, where you can see that a lot of the simulations actually end up with a very low recall, which would be bad for our review. However, our criterion generates some work savings while reliably actually yielding a very good recall target. And because our criterion is conservative, we actually miss the target only in about 1% of the cases. So concluding, we provide a stopping criterion that works with any machine learning model, I have to say, and it actually can also be included in any of the existing tools. We have here on this GitHub page some details if you are interested in the maths. We also have a paper on the criterion that you can easily find online. And actually, in recent months, we also tested this in practice, and we see that there are huge work savings for larger data sets. And we also want to continue work on this, making the test less conservative by using non-central hypergeometric distributions, and thus be able to even save more work in the screening process. Thank you.
Great, thank you so much for that. Were there any questions for Finn? Well, I know that there was a follow-up question for Jan in the Q&A from the last talk. How do you decide how much of the set you need to use for training and presumably validating the supervised ML relevance screening model?
Shall I answer this, or shall I type it into the Q&A?
I think either way would be fine.
Yeah, so on this question, we actually took a very pragmatic approach in terms of we started with the rule of thumbs from previous supervised machine learning studies of such form with 2,000 screen documents, and then of course you take 10% usually for your trainings for your test data set, and from there you see how good your classifier is, and as you've seen, we then continued labeling quite a few documents. So we had over 3,000 labeled documents to reach the kind of quality thresholds that we thought were appropriate.
Were there any more questions before we move on to Joshua's presentation? Okay, I guess with that said, our next talk is from Joshua. You have the floor, sir.
Thanks, Chris. Let me get this set up here. Let's see. Are you seeing the whole slide?
Yes, we can see it.
And when I flip through, Chris, can you see the next one?
Yep, we
Okay,
can.
perfect. All right, great. Well, thanks, Chris, for leading this. Thanks to my attendees. Great presentation so far. And thanks to all of you for joining us. For me, it's in the morning. I know it's all over the place for everybody else. My name is Josh Polanin. I'm a principal researcher at the American Institutes for Research. And I'm going to talk about MetaReviewer today. And let me just skip right to the end of the talk and tell you that MetaReviewer is a program that we hope is going to help solve some of the problems that people have in the data collection process for doing a systematic review and meta-analysis, and specifically that time-consuming process of creating a code book, creating a coding form for the data to go into, and then creating a system that multiple people can use simultaneously. There's a bunch of, there are some programs out there that are available, but I'll tell you why we think MetaReviewer is going to be helpful to you, even if you're using one of those. So it's currently in a beta testing phase, and it's free to use. And the beta testing phase lasts for about another month. So if you go to metareviewer.org and click that Try MetaReviewer button that you see in the bottom right-hand corner, you can sign up and have continuous access through the beta phase and after the beta phase closes as well. So usually I give a live demo, but given the speed round, I'm just going to show you a few quick screenshots of what it can do, and really hope to send you over to metareviewer.org to try it out. So let me just show you one quick thing about the background of this. And essentially I've said all of it, but we're trying to do away with people using spreadsheets or sometimes costly database specific or meta-analytic software, and create something that multiple users can access at the same time, and try to keep it as low cost as possible. Essentially, it's free right now. Not essentially, it is free right now. It'll likely be free for most people for the foreseeable future. Only people with like lots of resources and really big projects will ever have to pay for it. What does it look like? What can it do? Right now, it will assist you in the coding phase. And we're working on some screening applications as well. So, once you have your studies identified as eligible, taking those studies and extracting the information from them. So this is just the basic. I know it's kind of small. By the way, if you right-click on the video and allow the video to give you more options to see all of the options in the video, you can make the video full screen. It took me a little while to do that in the system. So if you can see this, you'll see that the first shot is just like a projects page. If you click on that, on the button to set up a new project, it takes you to basically a 5-step process where you name the project, add some users, and then it takes you to this coding form wizard. And this coding form wizard asks you a series of questions about what type of systematic review and meta-analysis you're conducting. And based on that, it creates what we call a coding form template in a Google document. And this Google document includes lots of, in fact, there's 50 preloaded items, potentially 50 preloaded items that are like the basics of doing a systematic review and meta-analysis, things like sample characteristics, outcome characteristics, intervention and program characteristics, and a whole host of effect size calculations that are set up for you. And the beauty of this Google document is that you don't have to work with the software itself. You don't have to know programming languages to create a coding form, something where people can actually interact with it on the screen. All you have to do is manipulate these tables in a Google document form. Once you manipulate the tables, you open up the project setup page, copy and paste the document ID, and then once you do that, MetaReviewer is going to import this coding form and actually create this coding form template, this Google document, and actually create a coding form for you. There's also a simple process for importing citations. So once you've created the project, this is what it looks like. You can access all of the studies and the citations. This is what the studies database looks like. Each one of these rows is clickable and allows you to see some more information about the study itself. This is what the coding form actually looks like. It's set up in a hierarchical relational database way. And I don't have time to talk about that. But that's the best practice for conducting and extracting a meta-analysis. And you can see that there's questions and little fields that you can fill out just like you would normally do, but fully accessible online. And then this is just a screenshot of some of the various types of effect size calculations that we have built in to the system. Lastly, I don't show you this, but once you're ready to do some data analysis or just take a look at your data, there's a little button that you click on that says export the CSV file, and it combines all of the data for you into one flat file that you could easily use to estimate effects or do your meta-analysis or whatever you need to do in any of the programs. And with that, just a shout out to the lots of staff that we've had tested this thing, especially Megan Austin, Ryan Williams. But we have lots of staff that have helped on the program, lots of developers, alpha testers. We received funding from the National Science Foundation, and we've had some great advisors along the way. So if this is of interest to you, again, go to MetaReviewer.org and sign up and let us know what you think.
Great, thank you so much for that. Were there any questions? I had one, but I'll save mine. I don't think there were any in the Q&A. Oh, so in the Q&A, Josh, you mentioned that you would compare it to other software.
Yeah.
It said, I understand that this is only for quantitative studies. Is that right?
So it is, I'm mainly a quantitative person and our team is mainly quantitative. So it is based on the experiences that I've had and that we've had. So it is primarily set up for quantitative, but it can easily be adapted to a non-quantitative systematic review in the spirit of like a quantitative systematic review, but it could also easily be used for a meta-synthesis or qualitative systematic review. It's just a coding form. I mean, it's a lot more than that because it can be used simultaneously by multiple people, and it's set up in a way that makes the extraction process easy and straightforward. But if you are doing a meta synthesis and you're using a spreadsheet or some other program that isn't designed specifically for systematic reviews, then this is going to be great for you.
And is it currently set up to handle multivariate meta-analyses?
Oh yeah, absolutely. Yeah, it's a hierarchical relational database. So you don't enter contrast by contrast like you would in a spreadsheet. You create records based on conditions or samples, and then once you extract information for effect sizes, you're extracting that information at the contrast level and identifying the appropriate samples, conditions, and outcomes one by one. But you're only identifying the IDs associated with those records and then identifying all of the appropriate effect size information. Once you export the data set, then it combines the file into one big flat file that we're used to working with in a spreadsheet, but you don't see all that extra information.
Is exported to like any file type, like
CSV
like
right
R
now,
or anything like R and Stata would take it.
Okay. Oh yeah, absolutely. It's a CSV file that I use in R, and yeah, easily manipulated in any program.
Okay, great.
Yeah. There was another question. If a user makes a
few, actually,
yeah. So Kate's question about making adaptations to the coding form, easily adaptable. We set it up so that the templates themselves you copy and paste into your own Google Drive, and then you manipulate those tables, copy, paste them, change them, add them. Yeah, we have I should also mention we have a lot of resources on MetaReviewer right now. We have a 70-page user's guide that walks through users on how to manipulate the coding form templates and get it all set up. So easily adaptable, Kate.
And then there's one from Michael. I mentioned that he discussed comparisons of MetaReviewer to other tools. I may have missed it, but didn't hear any of those.
Yeah. So it'll have the look and feel of some of the features of EpiReviewer, some of the features of Ryan, some of the features of Covidence. I mean, we're all doing similar things. So we're not purposefully copying or using their IP in any way. This is purely based off my own experiences as a longtime systematic review methodologist and a heavy user of meta-analysis. But the big differences are that it's free, it's browser-based, it's a hierarchical relational database. We have this codebook coding form template set up for you. All of the importing functionality and the automation that comes along with that is completely unique to us. The effect size drop-down thing is modeled after comprehensive meta-analysis. So if you're used to that, you'll see some of that. So there's pieces of it, but if you're really the group we were after is the novice or the person who is just getting into systematic review meta-analysis and is reaching for a spreadsheet, or if you're still using a spreadsheet for this purpose, then this tool is really for you.
Great. Well, trying to be mindful of time, I think it's probably best we move on to our next talk, which is by Heather. You have the floor.
All right. Let's see. Just wait for it to come up. Is it up now?
It is.
It is. And sorry, guys, just making my way around. And will it change slides now? Come on, change slides.
It is not changing slides.
Let's see. Now?
Now it is.
Okay, perfect. So my name's Heather Ames. I'm presenting on behalf of our machine learning team at the Norwegian Institute of Public Health. I am presenting from a slightly different perspective than the previous presenters in that I am a user. I am a medical anthropologist by training, and I specialized in qualitative evidence synthesis. So I work with implementation of machine learning methods within our group. So some of the other presenters have already said this, but we need high quality systematic reviews faster. COVID has really made this very evident to us. We need to do things faster, but not lose quality. And screening is the stage we identified that takes most of our time and is most intensive. So my team and I started two years ago to see how much time we could save screening by implementing machine learning functions available in EpiReviewer. So what we did is that we tested different functions independently and in combination across a bunch of systematic reviews on health and welfare interventions. We tested on full systematic reviews, scoping reviews, and some larger evidence and gap maps. So extremely large data sets, sort of 25,000, down to sort of much smaller data sets of 2,000. We used priority screening, which is a ranking algorithm. We used some pre-built study classifiers, design classifiers. We tested custom classifiers, and we used also some automatic text clustering. So researchers tracked their time in normal random screening, and we calculated a time per 100 studies to use as a baseline. And then we tracked our time and number of records screened when we then implemented these ML functions. So we found a time savings in the screening phase of 60% compared to screening as usual if we used priority screening or the ranking algorithm until our inclusion rate flattened out and then moved to single screening, but continued to screen all articles. And we did this for a while to kind of build confidence with our reviewers, but also to see, where we could then stop screening. We saved 90% or used 90% less time when we used multiple machine learning functions together, such as custom classifiers and switching to auto or single screening for studies under various cutoffs based on the classification. We found pretty good efficiency that 95% of our included studies were found after screening between 7.5% and 35% of the retrieved studies. This is down to, we thought that systematic reviews had very precise questions where the ranking algorithms functioned very, very well, where some of our larger scoping reviews and evidence maps are quite broad. So we had to screen quite a bit more to get to the point we thought that we needed to be. But the more efficient the priority screening was, the quicker we found everything. And we found some other benefits that I think would be interesting to research teams. And this was that using priority screening really forced us to narrow our inclusion criteria immediately in the screening process. So you flip your screening process where you're trying to find everything that's included first. And so we really have to sit as a team now and really go through the inclusion criteria, screen together a bit, go back to our commissioners and say, okay, this article's in the gray zone. What do you think? So it really helps us to prioritize things quickly, and it provides commissioners with estimates of project size quite quickly or quicker than before. And it's really highly accepted by the teams in-house. And it's also changed our workflow in that we, as I said, sit together to screen quite a bit more, and that helps. We move to single screening or deprioritize screening after we see certain cutoffs. And we begin full text screening in parallel to priority screening or title and abstract screening because we're identifying those articles so much earlier. And that's been very helpful as well. And now we're done screening within days or a few weeks instead of previously a few months. I remember I had a review with 12,000 hits a while ago that took us 3 months to get through. So it's really cut down the time we use on this phase. So we're adapting ML-supported approaches to screening and seeing a sort of 60 to 90% time savings. Again, we found 95% of all the included studies after 7.5 to 35% of screening the retrieved studies. We're able to maintain a high quality product, and working with machine learning has really changed the way our teams work and conduct our reviews. And these changes have been accepted by our researchers and our commissioners. And now as we're becoming more confident after 2 years of evaluating this process, we are becoming more confident in fully automating portions of screening, especially with the really, really large data sets. So I'm the implementation lead, so I have responsibility for teaching and implementation in-house and building capacity, and our innovation and evaluation lead is Lee Muller, so you can contact either of us at the email here. So I will stop sharing now and come out and see if there are any questions.
Any questions?
Yes. Jan, I see a hand.
Yeah, just sorry if I missed that, but I would be really interested. Did you at some point stop screening, or did you have the time savings purely from the faster pace you can go, because at the end you have this long tail and it's just no, exclude.
Yeah. So to build trust in-house, we had to go and single screen everything to the end for the first while, just to get researchers comfortable with the fact that this was working. And now but now after 2 years, I would say on average, very cautious teams might screen 1,000 without finding anything, which we're trying to get that number down. A lot of teams switch to single screening after 100 of not finding anything, and then single screen for 200 to 300. And if they still don't find anything, we either deprioritize screening if it's a systematic review where we need to find everything, or if it's like a massive gap map where we already have 900 included studies, then we say, no, that's fine. If we miss 10 studies, we're good. So we do have different sort of thresholds around product type as well.
Yeah, so just you may actually try the method that Finn did. It's a methodological way to actually stop, based on some.
Yeah, it's on our
criteria.
books. We're looking forward to trying it.
Exactly.
Yeah. It's on our to-do list.
More questions?
Well, if not, they get to listen to me for 5 more minutes and they can ask questions at the end of that, I guess.
I just have one question that I think I missed, Heather. What did you name a program that you're using, or what was
We're using Epi.
Oh, you used Epi. Okay. All right.
Yeah. We've
Gotcha.
been in talks. We've been helping out with Kadima. I'm not sure if there's Kadima people here. And then we're always exploring new options. So yeah, we're keeping our eyes open. All right. Well, then I will. Oh. Yes, Kate. Send me an email, not a problem. We can chat. We also find the thing with Epi is that you do have to have 5 included studies for the ranking algorithms to start. So for systematic reviews with very few included studies, we're not seeing the same benefits. And for really, really large scoping reviews, as you're mentioning, we do go a bit further. So we'll have to update our evaluation and see, but feel free to drop me an email. We can definitely chat. So then I'll share other presentation. And this presentation is much more about how we built and implemented our machine learning team in-house. So this is a shortened 5 minutes from a 2.5 hour workshop we gave. So yeah, very condensed. So we noticed under COVID that we needed to do things faster, as I said. So we introduced and scaled up ML among non-specialists through using off-the-shelf software. And we began with a 6-month team whose mandate was to explore the potential benefits of ML. So that was team 1.0. And here we're researchers with very, very backgrounds. None of us had a lot of machine learning, if any, experience. So we went through a fairly intensive onboarding process, peer review teaching, a lot of reading, getting ourselves up to date, focusing on what we needed to know, and focusing also on identifying early adopters in our organization. And then we focused also on building knowledge. So we wanted to, in order to build trust with our researchers, we wanted to evaluate or test any of these functions against our in-house protocols. So even if they had already been shown to be effective, like ranking algorithms or the study design classifiers, we still ran in-house evaluations so that we had data we could show to leadership and to other researchers about, this works with our in-house processes. So you can see in the first year, in the first 6 months, we trained 23 reviewers and librarians on 20 projects. We're on 7 machine learning functions. We estimate we saved about 1,100 hours in screening. 15 of our publications described machine learning, and we had multiple presentations, and we were able to publish a manuscript on auto clustering. And then we got to the sort of a threshold where we thought, okay, now we need to build further. We needed a lot more structure and routine around implementation. That's where I came in as the implementation lead. I moved from team member to implementation lead. And we needed to start providing a lot more support to teams to build capacity so that researchers could start to implement these functions independently. So I was added as the implementation lead. And I had the responsibility of quality controlling teaching materials, piloting them, and delivering. We had a machine learning week where we trained our whole group of 70 researchers, for example, across various functions. And then we have, we go in this circle. So we have an innovation lead, Lee, and she, along with a number of other of our team members, go out and look for new things that we should be testing. They find something that they feel we should test. That comes into our evaluation side of our team, where we run and evaluate those functions against in-house routines. And then once we identify and evaluate a function that should be implemented into our workflow, then we develop teaching materials, team support, and then capacity build. We also had to come with a clear change message and communication strategy in order for this to work. And the team really has to be willing to take risks and have things not work. So we developed conceptual training materials that explain how the function works. So what is a classifier? What is a ranking algorithm? What is NLP? And then we developed technical training materials that are sort of the click here, click here, click here. As I said in my previous presentation, ML has really impacted our workflow. So we're not only building trust in machine learning and the new functions we're introducing, but we're building trust in our researchers and an understanding of flexibility in how we work. So now we have teams that are much more flexible. And this has actually even gone over into how we conduct our reviews. We're beginning to look at sort of workflow changes and how they could be. And then creating the tailored training materials has really been good for us as well. Understanding those conceptual concepts, the technicals, and then discussing the impact on our workflow. So in conclusion, you need a really great team that's curious and creative and open-minded and open to new ideas and high-performing and likes taking risks. We had buy-in and vocal support from our management. We had to figure out how to build a plain language understanding of machine learning functions without oversimplifying them. And I have a background with Cochrane in plain language and summary, so that was helpful here. And then we had to figure out how to best teach the sort of conceptual versus technical. We had to get our early adopters on board. We had these in-house evaluations that were really helpful, that showed acceptability, feasibility, and time savings, so that our reviewers could feel ownership of these processes. And we had a very low threshold, or we still have a very low threshold for support and questions. And we have a clear set of protocols for evaluations and implementations, which also help us keep going. So we really feel it's possible to start from nothing and have an impact in a relatively short period of time. I think we're 2 years now. And we're always looking for people who need data sets or want to collaborate to contact us. So please, please do. And that's where I will stop here as well and come back to the screen. Yes. Hello, everyone.
Thank you so much.
2 minutes remaining.
Look at that.
Nice flash.
Were there any last questions before? I don't know what happens at 2 minutes. I guess it just ends automatically. But
maybe we'll see. We'll get kicked out.
Any questions?
So maybe helpful. We're fully willing to share sort of our evaluation templates, any of our implementation guidance, or how we deal with team support, or if anybody's interested in starting a similar team at their institution, just reach out to us, and we're here to help. We'd like to see other teams do it. So.
Okay. Well, great. I wanted to thank you all for joining. I guess this will be the end of the session. I hope you all have a good rest of the morning or afternoon or evening, wherever you all happen to be located.
Thank you, Chris. Thanks, everybody.
Yeah.